I see a 2 in the audience. That is correct. So basically, the 2-byte sequence, hex 94, hex C3, actually is amazingly common in Windows DLLs. And so it's pretty common that you'll find this sequence be able to get you, if EAX points to data that you control, which is pretty common as well, it'll get you right to your stack pointer pointing to data that you control now. And once you have control of the stack, that contains a return-oriented program, and or I'll say return-oriented exploit payload. And what this can be is either a full payload that does everything return-oriented, which is a lot of work. You probably want a compiler to help you do that, or you can do what I do, which is just make a return-oriented payload stage, which is just a small amount of code that will just make it so that you can execute your normal payload. So let's kind of review a little bit, just get in this right mindset. Let's go back to 1997, Return-to-libc. This was, Solar Designer described this technique and named it right after a number of systems, including Solaris, started implementing non-executable stacks because, of course, people believe that the root of the problem was executable code on the stack. Well, if all the libraries are loaded at known places, what you can do is, at least on x86, return to a function. And you abuse the fact that you return to a function in that shared library. And what you do is you abuse the fact that on x86, the function arguments are taken from the stack as well. And if you've already overwritten the stack, that function that you jump into will use the arguments from your controlled data. And what this effectively does is simulates a function call to that function with arguments that you control. So an example of that is you can call system and give it the address, give it a pointer to a string that you control. You can kind of find that in your environment, or you can do a number of things, and that'll essentially give you, let you execute a arbitrary string from the shell with just one return. And what's cool is you can even chain these together. So you can extend this technique a little bit, and because the stack unwinds upward and you've already overwritten a lot of it, you can simulate one function call and then another function call and then another. And the only thing that's difficult to do is to use the return value from one function as the arguments to the other. We're going to need some a little more advanced technique for that. But with that, if you don't need to do that, you can easily do this return chaining. And what you do is basically you just lay out the stack in a certain way that allow you to advance the stack pointer and kind of fix things up. And I'll kind of show you how this works. So if you look on the left, I'm going to show you kind of the assembly code that's executing. On the right, I'm going to show you the diagram of the stack, because everyone loves stack diagrams. And I love making them because I made like 100 of them for this. And you can see I'll have it highlighted where the actual stack pointer is pointing to and what data will get used. So first, we've executed a return. We've corrupted the stack, and we're executing a return that's using our chosen return address. And that takes us to the top of this function in a library. And it's going to use the standard function prologue that's going to save the frame pointer and so on. And eventually, it's going to use our arguments, which is pulling, again, from the stack that we control. And then as it's leaving, it's going to restore this frame pointer and then pop the next element off the stack, which is going to be the address of a small sequence of a pop-pop-ret that what we're going to use is to skip over the arguments on the stack so that we can realign the stack to our next fake stack frame to simulate the next function call. So it's going to skip over those and then call our next function. So that's basically how it works. So we all know all this. This is all very old. So let's go a little less old. Return-oriented programming is the name given to a technique that was published by Hovav Shakam in 2007. And the main idea here, which was instead of returning to the top of a function, let's return to random bytes in the text segment just out of sequence. And what we'll find is that because x86 allows unaligned instructions, there are many unintended instruction sequences in legitimate instructions. And I'll give, actually, this is an older technique that was a little lesser known called the borrowed code chunks technique by Sebastian Kramer. I think he did it in 2005, but I have that reference later on in my presentation. But here you can see the main idea is that assume an application actually has the instruction of moving this 32-bit constant into EAX. And that encodes into the 5-byte instruction sequence that you see below. Well, if you just skip the first byte and return to the last 4 bytes, what happens is this turns into the instruction sequence that stores EAX into ECX plus 8 and then returns. And this is the main idea here. We can find unintended instruction sequences in legitimate instructions. And all we need to do is find these unintended sequences anywhere in executable memory that we know where it is. That's at a static or a known location. So another way to understand this, to give credit to Dr. Raid's girlfriend, because Dr. Raid was writing a script to do this, and he explained it to her, and she's like, wait, That's just like a ransom note. And we're like, that's genius. Yes, exactly. So return-oriented programming is a lot like a ransom note. You're going through the newspaper, you're cutting out letters, and those are the unintended instruction sequences, and then you're combining them into words, and these are your return-oriented gadgets, to use the terminology. And then you combine those gadgets into an actual letter, or an actual note, and that's just like your return-oriented payload. So it's a really great way of explaining it. And to explain what a gadget is gadgets are ways of combining these unintended sequences along with data on the stack to perform a sort of higher level semantic action. So, some things that might be an example of a gadget is a sequence that will write a chosen 32-bit value to a chosen memory address, or another sequence that will do arithmetic operations on a piece of memory, or a sequence of returns that will actually simulate a function call. And basically what you're going to do is you're going to write your program out of these gadgets. So here's an example gadget here. So if you have 3 sequences, here's how we're going to combine them. The first one, you have a pop EAX ret that'll set EAX to a chosen value. Second one is a pop ECX ret that'll set ECX to another value. And the third one will store EAX into the memory just pointed to by ECX. And then now we have a store immediate value, or if you're an old Commodore 64 programmer, you think of this as a poke. Kind of here's basically how it works with yet another stack diagram. We're going to return pop EAX to dead beef, return again. Now we're going to set ECX to feed face. And then when we return to our third sequence, we're going to write dead beef into feed face. And return, and go on. So you can see how basically you can combine these gadgets actually perform useful things. Once you have these gadgets, you can do higher level computations. And this is what's been called a return-oriented program. And the idea here is you can actually write a compiler for this. And this is what the Havav Shakam's paper did. And the innovation there is he actually made it Turing complete. And so he has conditionals, he has loops, and he actually wrote a full C compiler and demonstrated that he could compile quicksort against the Linux libc. And so quicksort would be implemented by a bunch of random returns into libc, which is pretty cool. And there's been actually a lot more interesting work, such as the name's escaping me, but some other researchers, I think from Germany, at Usenix in the last year or two, presented a paper on writing a fully return-oriented rootkit, basically where they could implement traditional rootkit technology using only returns into loaded modules. And this kind of dispels the notion that like a rootkit has to involve hidden code in your kernel. Well, it's only using the code that's there. And the quote that actually I ripped from this paper that actually I think is a really important thing to realize is that preventing the introduction of malicious code is not enough to prevent the execution of malicious computations. As defenders, what we're trying to do is stop malicious computations and malicious actions. Introducing new malicious code is only the most expedient way to do this, not the only way. And so we need to focus on the end effects, not the end strategy, not the tactics. So let's talk about how to do it the easy way, and I call this BISC. So this is just a Ruby library that demonstrates how to build borrowed instruction programs. Here's where I reference Sebastian Kramer and his, where he originally did this for x86-64 on Linux. So the main ideas I used here is, one, I wanted to keep it simple. I wanted to make it analogous to a traditional assembler, just to kind of fit into a more traditional workflow, and try and also minimize the behind-the-scenes magic and make a lot of what happens explicit to the user, because I was writing this for myself. And one, I can write x86 assembly. That's not hard. So I'm not scared of an assembler. And I want to make it explicit what I'm doing, so I'm not bitten with weird bugs. And then for convenience, I'll let myself write macros. And there are several ways that this differs from traditional or what's been called return-oriented programming. The key distinction is that return-oriented programming is actually, to be pure return-oriented programming, requires a Turing-complete compiler. And my BISC toolkit is absolutely not Turing-complete because in your shellcode you rarely need conditionals, rarely need loops, so it actually is not all that necessary. And so again, this is just an assembler, and what it lets me do is write a borrowed instruction program with just assembly mnemonics that are found from the existing program. And so how it's going to work is, first I run a scanner on a variety of code modules, and what these will be, these will be like the DLLs that I know are loaded at a certain place, or DLLs that are just available. Or for instance, if I can use a memory address leak and then so I know that DLL X is at location Y, I can then scan it, assuming that that version of the DLL is at location Y, so that my return-oriented program will execute correctly. And my ROP generator is very fast. It executes in a split second, so it's easy enough to just do in a Metasploit module. So basically, the way that the scanner works is I'm being fully transparent on just how ghetto this actually is. The secret to doing return-oriented programming fast is binary regular expressions. Because I don't care about looking for every possible instruction. I just care about finding a small number of ones that I need. And so what I did is I just took the instruction encoding for a variety of, just the standard arithmetic operations, data transfers like move, and a few others, pushes and pops and so on, and then basically combine those into a regular expression for the instruction encoding. And then I just have a loop, combines them all into one big regex, and it just scans the text segment and spits out everything it found, which is pretty nice because it's, one, fast. And one example is I used this on Mac OS X, the Mac OS X version of Google Chrome, which is a 37 megabyte text section, and it'll scan the entire thing in 5 seconds on like a relatively modern laptop. So that's distinctly what I call fast enough. So here's sort of how it works. If we run it on a arbitrary module, it'll just print out all of the things that we can use. And I call this our vocabulary. And if you look, you can see there's a couple interesting ones. We have an exchange EAX ESP. It's kind of useful. We have a move ECX into EAX. That's our memory read. We have plenty of memory writes. We have plenty of pops to set registers. And so we can say, all right, yeah, we definitely have enough workable pieces here that I can construct a meaningful payload. And the other thing that BISC lets me do is, even though the stack unwinds upward, and so the memory addresses will go up, I want to write my program downward, just like a traditional assembly program, so that ideally I can look at the assembly and I'll understand it, because even though I won't be using the same instruction mnemonics that you would if you're just writing normal assembly, I'll be doing things in a similar way, so if I understand assembly, I understand what my program does just by looking at it. And one of the things to keep in mind is that you'll occasionally have to do workarounds. Because you are being very opportunistic on what instructions are actually available, you might not have the exact instruction that you need, so you will have to string together a sequence of instructions that are available that perform the equivalent function. So if you look at the bottom of the screen here, you can see on the right, I really wish I could just add 3 to memory pointed to by ECX. But unfortunately, that instruction, let's assume that instruction wasn't found. But the ones on the left were. And so I can say, all right, well, let's read from ECX into EDX, let's add 3 to it, and then let's store it. So it's a little bit roundabout, but it achieves the exact same thing. And so basically, I just write this as a Ruby library and kind of have this like intermediate language sort of syntax where my program is just an array. And elements in the array, if it's a string, that string gets looked up in a hash table to replace it with a memory address of that instruction followed by a ret. So keep in mind that I'm only looking for instructions followed by a ret. So whenever you see like a pop EAX, that'll be replaced with the memory address of a pop EAX ret. And another thing I forgot to point out is that I look for only very simple forms of instructions. If you looked at the x86 instructions, encoding and all this stuff, there's a lot of really wacky encoding types with prefixes, scale index bytes, displacements, all this stuff. And in order to make this simple, I just did away with that. So I only look for no displacements, no scale index bytes, no prefixes, just the bare instructions that I need, and that's actually usually enough. And when the day comes that that's not enough, I'll actually implement, add more functionality to the scanner to make it work. So these arrays also can be nested. So the nice thing about this is that it lets you write macros as just functions that'll return an array, and then that array gets embedded, and like the assembler just flattens it and assembles it. So it's pretty easy. And the macros let you write what I call higher order BISC. And if you think about how to do this, macros are like virtual methods for common high-level operations. What you're going to do is you're going to write, macros for my macros are kind of analogous to gadgets in return-oriented programming. And these will be things like set a variable to a value, do an arithmetic operation to a variable, so on. Call a function through a variety of ways. And what you do is you write your return-oriented program in terms of macros, not direct instructions. And so then if you retarget the generator to a different DLL, it may complain that certain instructions aren't found.